Hello everyone, today we will be going over the blind 75 in C++, and today we're working on lowest common ancestor of a binary search tree. Now, before we get started, make sure that we have our 4 questions that we all need to lay out accordingly. Let me just do one. Alright, we have our second, third, and fourth. We need to ask ourselves when breaking down the question what the input's going to be, what data structure / algorithm / technique we're going to use, what to do with the data, and then what our output is going to be. So now, breaking down the problem, given a binary search tree, find the lowest common ancestor node of 2 given nodes in a binary search tree. Okay, so we are given a binary search tree with the root, P and Q, which could represent the 2 nodes. And it looks like that we need to return the lowest common ancestor. And according to the definition of the lowest common ancestor in Wikipedia, the lowest common ancestor is defined between 2 nodes, P and Q, as the lowest in T that has both P and Q as descendants, where we allow a node to become a descendant of itself. Okay, so now, to be able to just break down everything that we have already just been discussing over here, so if we have our input right over here, root is equal to 6280479, and then null, 3 and 5, then we have P equal to 2, and then Q equal to 8, lowest common ancestor of nodes 2 and 8 is going to be 6 over here, given the fact we are working with a binary search tree. But then if we have the root of 6280479, null, 3, 5, P and Q, 2 and 4, 2 over here, and then we have 4. Accordingly, what is the lowest one that we would actually have this relation to? Well, according for this one, 2. The lowest common ancestor of nodes 2 and 4 is 2, since a node can be a descendant of itself according to the lowest common ancestor definition. Okay, so 2 and 1 accordingly. Alright, so it looks like that the lowest common ancestor refers to the root at the highest level possible. So meaning in particular that if we have, for example, 6 over here, P and Q, 2 and 8, they are both descendants of 6. The definition states the lowest common ancestor is defined between 2 nodes and the lowest node in T. That means that P and Q are descendants of it. And if 4 is a branch of 2, that means 2 will be the lowest common ancestor. Okay, so we need to replicate this behavior for the lowest common ancestor. Just clarifying on this. And so what we will be doing for our following steps accordingly is that from this we will be extrapolating on binary search tree properties on the relationship of the nodes we have, and in doing so we will traverse the tree and compare the values of the current node with the values of P and Q. Alright. And so, just to be able to go over the steps, we're going to first have our edge case that we need for the following. It looks like for the tree, what we would need to do is that, well, since we are already given a binary search tree, let me see if there are any other constraints as well. P does not equal to Q, and P and Q will exist in the binary search tree, and all the values of the nodes are going to be unique in this case. Okay. So, for an edge case that we would have, we will need to return a null pointer if we have a null root / node of the tree. That will be our edge case. And then what we will be doing next is that we will start traversing the binary search tree from the root, assuming we have a value. Then what we will be doing next is that while traversing, we're going to compare the values of the current node with the values of P and Q. And then, if both P and Q are smaller than the current node value, we're going to move to the left child. Then if both P and Q are greater than the current node's value, move to the right child. And then if neither of the above conditions are true, it means the current node is the lowest common ancestor, which means therefore return the current node in those edge cases. So we will have it from the left side, right side comparison. And so now to be able to just go over the steps, step 1, step 2, I'm going to leave step 1 over here to start with, and what we need to do in this case, I want to put step 1 over here, and we will be returning a null pointer just in case. I know this may be a little bit tricky at first, but then what we will need to do is that it will help us expand more upon our relationship. So the first thing we will need to do for step 2 then is we'll have tree node will represent the current node. Yeah, okay. It's going to be the root. And while the current node doesn't equal null pointer, we're going to expand upon step 3, step 4, step 5, and step 6. So step 3. Okay. Step 3. We're going to compare the values of the current node with the values of P and Q. So that means P's value is going to be less than the current node, which would have the value, and P will be the value where we are comparing the current node with its value. Just want to clarify that so that we have P and Q for them. Yep. I'm sure I got this right. There we go. Now for the next step that we would need is that we're going to be setting step 4. If P and Q are smaller than the current node's value, move to left child. So that means current node accordingly. So we have this case over here. This will be step 3 actually. This will be step 4. Yep. Since we're making our comparison accordingly, if we have current node is going to be current node to the left. Okay, now, and then this will be step 5 accordingly for this edge case. Where it will be the same, except for it's going to be greater than. Right over here. That current node is going to be the current node on its right. And then for step 6, what we will do is that we're going to have our else case. And then if neither of the conditions are true, we then assume that we have the current node be the lowest common ancestor accordingly. So just want to be sure we get everything right. Yep. And then, yes, no pointer right here. I'm just going to clean up the rest of the notes for you folks so that way you can see it thoroughly. Mm-hmm. Accordingly, and I'll have these in the comment section as well, so you folks can also follow along. Let me just double check to see if it's all right. We compare the left, and then we compare the right, and then we assume at the same time, okay, in the worst case, we'll return null. Okay, I have an extra bracket that's already right here. Yeah, not needed. Not needed. Yep, okay. Alright, passes all the test cases. Alright, and it runs efficiently. So to give a breakdown on the space and time complexity for our following solution is that our time complexity is going to be relative to the height of the binary tree, so therefore the complexity for our solution is going to be O of h, given the fact that we are currently storing the value of a current node accordingly, so that's why it would be constant, and it's all relative to the height of our tree to be able to find our lowest common ancestor. And luckily, since we are not using a data structure to be able to store our given values, our time complexity for the following is going to be O of 1, since the algorithm only uses a constant amount of extra space for storing the current node and just compares the values accordingly, since, again, we're not using another data structure. So yeah, this was lowest common ancestor of a binary search tree. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you also have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye.